Let's continue talking about first law of thermodynamics. Again, we've said this is a kind of a simplified version of the first law of thermodynamics. This is a lot better than the raw differential equation form that says the rate of energy in minus the rate of energy out is equal to the change in the energy of our system with respect to time. This is kind of the rawest, most pure form of the first law. We'll simplify it to this, and basically you see what I don't know if you see what I've done here. I've moved the delta t, or the change in time, over here multiplied by the rates, and that just gives me the total energy in minus the total energy out. That equals the change in energy of the system. And I said, don't try to memorize this long equation. Break it down to its pieces. Okay. Now let's look at some of these pieces. So let's talk about today. Let's talk about in basically what would be the equivalent of lecture 4. Let's talk about heat and work, and different kinds of heat and work. Okay. So if we talk about heat transfer first, as we mentioned, heat transfer is I would say brought to you by the letter Q, or sponsored by the letter Q. This is a lowercase q. Again, if I've got a total quantity, like the total amount of heat transfer, and I divide that by the amount of mass, then I use a lowercase q to represent the energy per unit mass, or the per unit mass version of larger variable, or the capital letter variable. So Q is no different. This is heat per unit mass. This is heat divided by mass. The subscript 1, 2, that's just simply telling me for a process going from state 2 to from state 1 to state 2 that a lot of times we'll use 2 and 1 as my final and my initial, because we'll get later in the course we'll get into multi-step processes to where you'll have state 3 and state 4. So final and initial doesn't always make sense for us. There's not always just 2 states. So that's what the 1, 2, you'll see that from time to time. Don't use it too often personally, but it's there. Okay. So important definition here. I'm going to write this. Anytime I write something on the notes, it's because it's like really important. I mean, it's important enough it's made it to the PowerPoint slides, but if I'm going to write it by hand, that means that's really critical. If I've got a system or a process that is what's called adiabatic, that's just a fancy way of saying that there is no heat transfer occurring. Okay. Other ways that can be said is the problem statement might tell you it's a well-insulated system, or they may just simply tell you to neglect the heat transfer somehow. But those are kind of the main ways that this text will tell you to neglect the heat transfers. They'll either tell you it's adiabatic, they'll use that as an adjective, they'll tell you it's well insulated, or they'll just outright tell you don't worry about the heat transfer. Now sometimes in chapter 2 we just simply say, well, we don't have any tools to find the heat transfer, so we're just going to have to neglect it, or we're going to have to make the assumption it's negligible. That works in chapter 2. It doesn't work very well in chapter 4 and beyond. We'll talk more about that as we go along. So in this slide here, it's just like we saw earlier. If I put a dot above a variable, that means that variable is being measured per unit time. That's a rate. So if they give me Q dot, that they're telling me the rate at which heat is being moved, right? To find the total amount of Q, I just need to integrate that Q dot, that rate, with respect to time. Now, I don't like necessarily the red ink. I'll say if Q dot is constant, right? So if you find a situation, this is a pretty common situation, it's kind of a special case. We always know we can integrate it. Something that's a function of time, we always know we can integrate it over time to get the total amount. If I've got a rate as a function of time, I can integrate that with respect to time and get a total amount. If I know velocity as a function of time, I can integrate that and get displacement. Or acceleration as a function of time, I can integrate that and get velocity, right? That's simple physics, or at least calculus-based physics. Same idea here. If I know the rate of heat transfer, I can integrate that over a period of time, and that'll tell me the total amount of heat transfer during that time. Now, the easiest integral to do, in my opinion, is the constant. So if q dot is constant, it's not actually a function of time. It's just q dot will just multiply by the amount of time, and that'll give you the total amount. So I've got heat transfer at a constant rate. It's kind of one way to say that. And that's an easy integral to do. Okay? And that's the most common scenario we'll deal with. You might deal with q as some exponential to a power of time, and probably a negative power of time. But this is kind of the most common scenario, is if I've got heat occurring at a constant rate. Then it's a real simple integral. But we need to understand how that works. Okay, so we're not going to go real in-depth on heat transfer here. We're going to give you kind of the brief overview. Most of you are going to go on to take a junior level engineering course in heat transfer, where we spend a 3-hour course looking at how do you model heat transfer, how can we estimate it. It's not simple, it's not trivial at all. So for us, we don't have that toolkit in place yet. So for us, we're just going to say Q is normally something I'm solving for. It's probably what the problem's asking for, so I'm probably either going to solve the first or second law for the unknown heat and move on. But that doesn't mean we can't talk about the basic theory behind heat transfer, right? So the basic idea of heat transfer is it occurs in one of 3 ways. You have conduction. Conduction is where one molecule or one atom or one particle passes energy directly to the particles next to it. So you've got one excited atom, we'll say, and that atom gets excited and that starts bumping around and moving around and oscillating and jumping back and forth, and that bumps into the atoms next to it, and that gets them excited. They start bumping up and down to kind of move with that atom or move away from it, and then they start bumping into the atoms next to them or the molecules next to them, and eventually the energy gets passed from a really highly agitated, highly excited molecular atom, and that energy passes through the chain to the next ones, and then the next ones, and the next ones. That's conduction. The heat is being conducted from one particle to the next. Convection, that's where you've got a group of particles. They sweep through, they move through, and as they move through, they impart energy onto whatever they come in contact with, or if they come in contact with higher energy objects, they'll remove energy from whatever they come in contact with. And what determines the direction of that energy transfer is the temperature. So if the fluid is colder than whatever it comes in contact with, convection will occur where the fluid is cooling the object. Right? The fluid is moving heat away from the object. That's Q out. If the fluid is at a higher temperature, then it will add heat. It will put Q into whatever it comes in contact with. Okay? Both of these require some kind of a medium. That requires molecule to molecule or atom to atom contact. One has to be in contact with the other. This one does not. Radiation can occur essentially in a vacuum. We're constantly being bombarded with solar radiation. That's really where most, if not all, of our energy comes from on Earth. At some point in time came from the reaction, the nuclear reaction that's going on in the sun right now. That emits radiation that gets the sun really, really hot, and that very high temperature body emits lots and lots of energy. Now, I'm not an expert here, but from what I understand, basically an object, when it radiates heat, it's emitting small particles, many times subatomic particles, that are very, very high energy. They can travel very long distances, and when they come in contact, when they strike something else, the energy that high energy subatomic particle is carrying is then transmitted into whatever it hits. And so if you have enough of these really high energy radiation particles bombarding another object, eventually that object's going to heat up. It's going to gain energy through that radiation process. Again, these can occur, these require one medium to be in contact with another one. Radiation does not. Radiation can be emitted long distances through a vacuum, through space, through outer space, does not require something in contact with something else. Just requires a temperature difference. Now, all three of them require a temperature difference, but that's really all the radiation requires is a temperature difference. Okay. The application of of force over a distance. That is work. So in a physics class, they may have taught you work is equal to F force times distance, right? Well, that's only partially true. It's actually the integral of force with respect to distance. I'm hoping they talked to you about that it's actually the integral. The net result of that force as it varies as it is applied throughout the distance. Most of the time we'll encounter constant forces, so most of the time this is a very simple integral. Most of the time it's just F times distance, force times distance. That gives us work. But it's important we understand it is an integral. It's just F is typically constant, and that's okay. Work done per unit time is what we call power. Power has units of watts or kilowatts or horsepower. Right? Horsepower is the English or imperial system version of power units. We typically reserve the term power for a work rate, W dot. We don't normally apply power to a heat rate or any other kind of energy rate. Normally we reserve the term power for a work rate. Now, I'm not going to count you wrong or anything like that if you do call a heat rate a power term. It's important kind of technical difference there. Power represents the rate at which work is being done to a system or extracted from a system. To get the work, again, we would need to integrate that power with respect to time. So if you integrate the rate with respect to time, you get the total amount. That's physics. Right? Same thing applies here. It's just instead of distance per time, we're talking about energy per time, or work per time. Okay. Now, I don't know if you notice in your text. I'm hoping you have noticed. I'm going to look and see if I can find an example here quickly, so I know exactly what he's using here. Sometimes you'll see these strange-looking symbols in the text. Here we go. You see this symbol right here, right? Next to the W there. I call that a del. It is a D. That is a version of D, the inexact differential. And most of the time when I draw that, I'll draw it something like that. Okay. So you might see this is a dW and this is a dQ. Okay. And so this del, which we'll refer to as a D, that's what we call an inexact differential. Now, I'm not assuming at this point you've had differential equations, and they don't normally talk about inexacts in the lower level calculus courses. So just so you know, the regular D is what we call an exact differential. What that means is we know it's a function of one variable. If I use a regular D, we know we're dealing with a function of one variable. We only use a regular D, an exact differential, if we know it's a function of one variable. Now, those of you who've had a multivariable calculus course, you've probably used the partial differential. The partial differential is when we know it's a function of more than one variable. Okay, and on the next video, we're going to talk about the inexact.